Hi, how's it going? My name is Carl Diaz. I'm with the University of Colorado, Denver, and today we're going to be talking about some concepts associated with work. So let's get going with that. All right, so over here we have a situation where three balls are being thrown off a cliff. One's being thrown at an angle, one's being thrown directly off, and one's being thrown down. Okay, and there's some questions about what their speed's going to be down here. Okay, so we want to figure that out. We know that all three balls have start with the same velocity and have the same mass. All right, so they weigh the same, they both start with the same speed. We want to know what their speeds will be down here. Well, for the first two, right, if they have the same, starting with the same speed and they're starting from the same height, they have the same kinetic energy and same potential energy. They have to, because potential energy comes from height, kinetic energy comes from speed. If it's the same speed and same height, no matter what direction they were thrown, they start with the same amount of those, and then when they hit the ground, there's no more potential energy for both of them, but there's all their, or what I should say is all their potential energies has converted in kinetic energy down at the bottom, so there's no more potential energy left. So we know when we start with our initial equation of K initial plus U initial equals K final plus U final, it'll be the same for ball 1 and 2, and that's what we're saying here, right? Because they're going through the same height, same velocity, where the final potential energy will be 0, so we have a final equation of K initial plus U initial equals K final for both ball 1 and 2, because they're so thrown from at the same speed from the same height. And since that's all these equations are talking about, we know that they're going to have the same equation, right? Where the initial kinetic energy will be equal to 1/2 mv squared, initial potential energy is mgh, and the final kinetic energy is 1/2 mv squared, right? We cancel all those m's out, we're left with this equation, right? Where then we want to solve it for the final velocity. We're looking for final velocity here. I should have put that in here. This is final velocity, because that's initial velocity that we have in that equation there, right? We're trying to solve these for final velocity. And we see that once we solve this equation for this final velocity over here, that 2 is going to come over 2 times all of this, right? Oops. That should be 2 times 1/2 v squared. Let me just rewrite that real quick. It's 2 times 1/2 v squared initial plus gh, but keep, right, and they're all thrown with the same velocity, 3.5 meters per second. They don't tell us, but let's say all their initial velocity is 3.5 meters per second. So that's what would go in there in the initial velocity. And then the gravity times height, all under the square root, right? And all of that times 2 under the square root would be the final velocity for both balls, both ball 1 and 2, no matter if it was thrown directly down or kind of thrown out. Since they both went through the same height displacement, and that's what this is trying to tell us, they have the same velocity, because speed down here, right? When the mass cancels like that, we see speed as mass independent, so their weights don't matter. And it really was just based off their initial speed, right? Because this is initial velocity. Their initial speed and their initial height is what's going to dictate their velocity at the bottom. They were thrown at the initial speed that was the same, and their height displacement's the same, which is what this equation is telling us. They're going to have the same final velocity. But what about 3? 3's thrown up. It gets some potential energy, right? But then it also kind of loses it. You should see that, right? The same potential energy that was gained is now lost, right? So when we write for part 1, that first part, we want to call this first part up here part 1 for ball 3, and then this second half will be part 2 for ball 3. Okay, but for part 1, right, since we don't start with any potential energy and we get back to the same height as which we were thrown at, that means that there was no change in potential energy, right? There was no height. If we would have stopped up here, there'd be a difference in potential energy, right? But since we come back to the same height we were, there's no height displacement in terms of this first reference point, right? This is our first reference point for part 1. And so for our reference point for part 1, there's no height displacement because we come back to the original place of where we threw it from, right? So we show that with part 1, right? We start with kinetic initial plus U initial equals K final plus U final, right? Where we see the initial potential energy 0, and in terms of our reference spot, which is right here, let me do that in a different color, right? So we got a different, this is our reference spot for point 1, this is our reference spot for 2, second reference point. This is our first reference point for part 1, for part 1 for ball 3, okay? So we see that it starts with kinetic because it has velocity. It's thrown with a certain velocity, right? Has kinetic energy, but no potential energy in terms of our reference height. It's like it's starting on the ground, right? And then when it comes back over here, right, and we look at it over here, it has kinetic energy again, but no more potential energy because all the potential energy again went back into its kinetic energy over here, right? So we see there's no potential energy over here in terms of our reference point, right? So we're just left with K initial and K final because in terms of our reference point, there's no height displacement. So for our first part, it's K initial equals K final. Well, that's just telling us that the initial kinetic energy is equal to the final. And if that's talking about velocity, we're saying that the initial velocity is equal to the final velocity. So really, this didn't mean anything in terms of what it's going to do down here because it's really coming back to the same speed that it was thrown at. But we know that from our projectile motion kinetics, right? Whatever speed it was thrown at, when it comes back to the same height, that's the speed that it's at again, right? So we know it's really just at the same speed over here that it was over here. So it's really just like if I threw it like one of these balls, I just threw it straight down, right? Because it's really just at the same speed that these two balls were, right? At the same height, right? Here, this is ball 3, right? It has the same velocity as ball 2 and ball 1, right? Because they were thrown at the velocity at that point. So it's also thrown at the same velocity as those two. And if that's the same velocity as over here, and it's still the same velocity as 1 and 2. All right, so that's what this is saying, that it's at the same velocity, same initial velocity, same final velocity, okay? So that, right, when we go to do the second part in terms of our conservation of energy, we want to say, okay, we have kinetic energy, but that kinetic energy is the same kinetic energy that 1 and 2 had, because kinetic energy is 1/2 v squared. If their masses are the same, and if this speed is the same as these two, as 1 and 2 over here, it means their kinetic energies are the same, right? So we start with the same equation, right? But instead, right, we know that right here I have some, in terms of my second part, right? This is my second reference point. I have some height difference here, but it's the same height difference as 1 and 2, right? So that's important to see too. So at the beginning I have initial kinetic energy, I have some speed, ball 3, initial potential energy because I have some height in terms of my reference point. But when I get down here, I won't have any more height in terms of my reference point, but I'll be moving, I'll have some speed. So final potential energy will be 0. We write that equation, it looks very similar to this one. Look, they're the same one. And when we solve it, look, we end up with the same thing, right? Where the initial velocity in here will be the initial velocity here because they're going to be equal, right? This final velocity would be the initial velocity in here, but this final velocity and initial velocity are equal, not 0. They're equal, so it doesn't matter which one you put in here. But technically, right, the initial velocity was over here, the final velocity for ball 3 is over here, but they're going to be the same speed. The initial velocity for ball 3, just remember, the initial velocity for ball 3 is equal to the final velocity of ball 3 over just right here. Not down here, but right here. So that means that that initial velocity in this equation to solve for the final velocity down here will be the speed that it was thrown with over here since they're going to be the same. So that means that this equation and this equation, they're identical. Even the numbers, the initial velocity, oops, look, I did the same thing that I did up here, down here. This just needs to be 1/2 v squared initial plus gh. I don't know how I didn't put the 1/2s in either of those, right? But we see they're the same equation. They're going to have the same numbers in them because the initial velocity and this velocity over here, they're the same. Do you understand that? Because of this. This is telling us right here that if they're, right, their kinetic energies are the same. Make sure you see the difference between part 1 and part 2 here, okay? Their kinetic energies are the same. That means if they're the same masses, that means their velocities are the same too. So that means this velocity down here, even though it says initial velocity, it's this final velocity, but they're going to be the same. I keep repeating that so you understand that. If you don't understand what I mean, watch that part over and over so you understand, because it's about reference point. The speed here and speed that ball 3 left with will be equal. That's what we're saying, okay, right here. It's just this, not this final velocity. So maybe I should erase that. Because it's just this initial velocity for part 1 and the final velocity for part 1 will be equal. That's what this is saying. All right, I'll stop. Okay, but just keep that in mind because I know that can be confusing. All right, for this next one we have 2 boxes, but they're different masses. Mass 1 or box 1 weighs twice as less, or we could say box 2, mass 2 weighs twice as more as box 1. So mass 2 weighs more, or box 2 weighs more than mass 1, but they're pushed with the same amount of force. So equal force was applied to them, and they were pushed across the same distance. So distance and force was the same here, right? So this is saying displacement for x1 and x2 is the same, the pushes are the same, the masses aren't, right? Now we already know in our heads that if I put the same amount of force, let's say I have a giant boulder that's 300 pounds and a tiny little rock, if I put the same force into them, the boulder will not move nowhere near as fast as the small rock, right? So we know that their velocities aren't going to be the same. Over here we're talking about same velocities, right? We know that if they go through the same height displacement, they start, the concept over here to bring through this whole thing is that when they start with the same velocity and go through the same height displacement, they will have the same velocity down here at the bottom. That's a concept, write that down. Write that down. If they start with the same velocity and go through the same height displacement, right? Because we said this height displacement cancels out, so they're essentially all going through the same height displacement. They're going to have the same speed. Well, over here, we're pushed with the same force and have the same displacement, but since their masses aren't the same, okay, we know this one will move much slower than that. That's significant to kind of know, all right? But what we want to know is if they experience the same change in K. Do they have the same change in kinetic energy? All right, and we can ask the same thing over here, actually. We'll do that over here in a second with the balls, see if the balls have the same change in kinetic energy, all right? So what we do, since we don't know the velocities over here, right? We know they're different, but we don't know their exact numbers. We want to use the amount of work being done on the object. And we know work is equal to the change in kinetic energy, so we can make these two equations equal to themselves, okay? And we can look at the force, the net force and the displacement on these two things, okay? We know for both of these, they're both moving this way. Force and displacement, right? This is force and they're in the same direction. So that means cosine theta just turns into +1, so it drops off. Okay, that's what I'm saying here, right? And again, I just have one equation for both boxes because why would you need two, right? If they have the same force applied to them and the same displacement, and we're just using this equation, which is this, it's going to be the same for both boxes. I don't need to do two different, I don't need to do the work twice. Do you see what I'm saying? If you don't, make sure you understand. Okay, since they're both equal to work, right? I can say that the force on displacement cosine theta is equal to the change in K, because we're looking, the question was here, is the change in K the same? I can't write that, but the question for these two boxes was, do they have the same change in kinetic energy, right? Well, we know we can't look at their velocities, but if we look at the amount of force and displacement, the amount of force that was applied to these two boxes were the same, and their displacements were the same, and that's all this equation is based off of, then their change in K has to be the same. But don't say, what the heck? How can that be true? How can they have the same change in kinetic energy they don't want? Well, think about it. Kinetic energy is 1/2 mv squared, right? So the velocity for these two things are going to be much different. So for one of them, right, the kinetic energy when they get over here is going to be 1/2 mv squared for this box. And when it gets over here, it's going to be 1/2 mv squared for this box, right? But this one's m is small, but the v will be large. For this one, the m's large, but the v will be small, and it's because of that, these will be equal. They'll have the same kinetic energy because the velocity for this one will be larger, but the mass will be smaller, but for this one, the mass is smaller, the velocity is smaller. That difference will be the same. These will be the same number, but we don't have to, that's what this is telling us, right? But we don't need to know the velocities to do that because this is telling us the same thing. Why? Because the amount of work done on both of these objects was the same. And if the amount of work done on both of these objects is the same, then the change in kinetic energy is the same. We could have said that from the very beginning and been done. But we proved it with this equation, so you need to know this equation. That's the work to prove that the change in kinetic energy is equal to the amount of work, the total work done on an object, right? But we can see that, right? We can see that through just the amount of force and displacement. The same amount of force and same amount of displacement, no matter their mass is applied to the object, their change in K will be the work. Their change in kinetic energy will be the same because that's the same amount of work being done on the object, okay? That's important to know. But what about the change in kinetic energy for the balls? We didn't look at that, right? Because this is where the masses are different, right? But so we have different masses, right? Different velocities. Here, we had same, right? All balls have same masses And we saw that the balls all start with the same velocity and they all end with the same velocity over here, right? So do they have the same change in kinetic energy? Well, here, right, we have an idea about their velocity, so we can kind of set it up a little bit different, right? We know for both of these equations, both of these balls, they have the same equation, right, to essentially solve for their final velocity down here at the bottom of the cliff, right? So we can just use that one equation for both of them, since it's going to describe both of them, right? And bring K initial over. When I bring K initial over, K final minus K initial is what? Change in kinetic energy, right? So I see the U initial is equal to the change in kinetic energy. I can just change that to change in kinetic energy. And again, if this is the same equation for all three balls, I can say that all three balls are going to have the same equation then, that initial potential energy is equal to the change in K. Well, if they all have the same mass and they all went through the same height displacement, which is what we said, right? This height displacement cancels out, as we talked about and showed in the math, right? So really, all balls, even though this one went like this, all balls really just went through this height displacement, all of them. Every single one of them just had this height displacement, right? They have the same mass. That means they all have the same change in K, all right? And what do we know? Change in K is also equal to the net work. So we can say they all have the same net work done to them, okay? And that would be equal to mgh, right? Because U initial gravitational is mgh, right? So we just swapped it into that, and the change in K is equal to mgh. For both of these, and again, all the same masses, all the same height displacements, so the change in kinetic energy for all three balls were the same. All right, so we can see two different ways to solve for the change in kinetic energy of an object and the net work done on those objects, right? This one's for the balls. This one's for both boxes, even though they have different masses, since they have the same force and same displacement. It's the same work for both, right? So you want to do, when you write this down on your paper, which is what you're doing, right? This needs to, you want to have this work for that box, so have this picture with this work next to it, and then have this picture with this work next to it. It's going to be the same work, but you want to make sure that both pictures you know is this work. So draw this picture, do all this work next to it. Draw this picture and do all this work next to it. Two pictures, two works, but the works are going to look the same. But it's to prove something, that the change in kinetic energy for these were the same. All right, this last question here is about two skaters. They're going down different slopes. One goes down a way, right? This one's way steeper than this slope, right? And they're going to go down. They have different masses. This person has a much larger mass than this person, but they're both starting at zero velocity coming down here, okay? The first question they ask is, are these skaters going to have the same speed at the bottom? Well, we've kind of already answered that in terms of concept, right? We said it right here. We said it over here, right? But what did we talk about? What was the point of this conversation here? Do you remember? When the mass is canceled, right? Velocity, we can see in these equations, that's important. Velocity is mass independent, okay? We can see that, it's important. We'll see it over here, but we see velocity is mass independent. We saw it also in our kinematics equation. There's no mass in the kinematics equations, those solve for speed, so we know that velocity or speed is mass independent. So no matter the mass of these people, we've learned from this that their velocity down here is just based off their height displacement. That's a concept we learned from conservation of energy. Since the hill's the same height, even though the slopes aren't the same, the hill's the same height, so they've gone through the same height displacement when they got in the bottom, that means that we already know that yes, they will have the same velocity, okay? Because the concept is they go through the same height displacement no matter what their mass is. If they started at the same speed and go through the same height displacement, they'll have the same velocity at the bottom. But we can prove it, right? So again, I didn't do two different works for these skaters because it's the same work for both skaters. So what should you do? Have both skaters. You want to do this work for one skater, and then on the other side, do this work for the other skater, but it'll be the same, right? We know both skaters will start with the equation of K initial plus U initial equals K final plus U final, right? But both skaters, right at the beginning, they have zero velocity, so zero kinetic energy, right? But they have height displacement, so they're going to have some potential gravitational energy at the beginning. When they get to the bottom, they're going to all that potential energy from the top will have converted into the kinetic, and then they'll have no more potential because there's no more height displacement when they get down here. So no more final potential energy. So initial kinetic energy and final potential energy are zero for both of these skaters, we don't need to write it twice. That's just being redundant, right? If they weren't the same, we'd want to write it twice, but it's true for both of them. We don't need to do it twice. Save time. So we know U initial is equal to K final for both of these, right? When we expand that out, where U initial changes to mgh and Kf turns into 1/2 mv squared, we see again mass cancels. When mass cancels, that means speed is mass independent, not kinetic energy, not anything else, just speed. Speed is mass independent. Speed is mass independent, speed is mass independent, okay? Not kinetic energy or anything. We can see kinetic energy has mass in it, so it's mass dependent, okay? But not velocity. So, again, this is the same work for both skaters. So at the bottom of the hill, both skaters are going to have the velocity of the square root 2gh, right? You see that? Let me make sure I do that in a different color. There's a lot of black on here. It can get hard to see. But this is the final equation for both skaters. Now again, I didn't do two work, but I want you to. You need to do both work. So you need to have the same work. It's the same for both. They're going to have the same equation for both skaters. Just do it twice so that you know that this skater's, that's for this work, this skater has the same work so that you know, I know, and I'm telling you right now in the video, so now you know, so there's no confusion that this work is the same for both skaters, right? Just like we were kind of saying over here, this work is the same for both skaters. This is the same work for both boxes, so there's no need to do them both. So they're going to have the same velocity because they're both having the same gravity, experiencing the same gravity, and since they're all going through the same height, it means they'll have the same velocity at the bottom. That's what this means, okay? Now, will they have the same kinetic energy at the bottom? Well, what did we just say? Kinetic energy is mass dependent. Velocity is not mass dependent, but kinetic energy is. So for both of these, we're going to have to write two different kinetic energies, right? We'll call this, since this is M1, we'll call this M1, right? Or this K1, and this is M2, so we'll call this K2, right? So for the first skater, K1 equals 1/2 M1v squared. Now we know in both of these equations, velocity is going to be the same because we said at the bottom down here, they're going to have full kinetic energy, no more potential energy, and their velocities will both be the same down here for both skaters, right? So both these V's will be the same. So the difference between these kinetic energies are in the masses. And we said M1 is 20 kilograms, where M2 is 10 kilograms. So this one's much larger, so K1, this person's going to have much more kinetic energy down here than K2 or the smaller person, okay? Their velocities will be the same, but their kinetic energies won't be the same, okay? This is their kinetic energies at the bottom. It's based off of mass since their velocities will be the same, all right? Now, what about their changes in kinetic energy? Well, that's important too, and there's three ways to look at it, right? We can just start with the change in K is equal to final minus initial, right? Expand that out, change in K is 1/2 mv squared final minus 1/2 mv squared initial, where we know they both start at zero velocity, so their initial kinetic energy for both of them is zero. So I'm not doing two works, but this is the same work for both skaters, so you should do this work for both skaters, even though it's the same equation, all right? We know this is zero, okay? So let me make sure that you can see the difference between these, because that might be hard, right? Because these are all three different ways to solve for the change in K for the skater, okay? This one down here is for the balls. So, after we see that 1/2 mv squared initial is zero, because both their velocities are zero at the beginning, we see that the change in K for both of them is equal to their final kinetic energy, right? Where it's mass dependent. Now, their final kinetic energy, we said it wasn't going to be the same because even though their velocities are the same, their masses are different, so that's the same here. But it's also their change, right? We started with the change. The initial was zero, so their change was just based off the final kinetic energy. Don't think it's always like that. If we had some initial speed here, it would be a difference between both. But since it's zero, it's just equal to the final, so the change in K is equal to just 1/2 mv squared. Okay, final, we know that even though their velocities are the same, their masses aren't the same, so they won't have the same change in kinetic energy. So they don't have the same kinetic energy, nor do they have the same change in kinetic energy. They're different answers. Even though they look very similar, they're not the same, because this was the change we were trying to find. This is just the individual kinetic energies at the bottom, all right? And since we know change in kinetic energy is equal to work, that's also the amount of work being done on these guys, right? So since the amount of work is also based off of mass, we can see that there's more work being done on the larger person than the smaller person, that should make more sense because gravity has to pull harder on the larger person to make sure they're the same speed down here, and that's a concept, okay? Gravity does more work on larger objects. We know that because at the bottom, if they go through the same height displacement, we know that it's mass independent, so gravity must be pulling harder on the larger object to make sure that it does have the same speed as the smaller object down here. If gravity didn't pull as hard on the larger object, the smaller object would move faster. But since gravity has to do more work, it actually pulls harder on the larger object, and they end up falling at the same rate, right? Or making it to the bottom. I'm sorry, not falling at the same rate, falling at the same speed. They end up making it the same speed. Because not only at the bottom are they at the same speed, right there they're at the same speed. So when they both reach that point, they're at the same speed. When they both reach that point, they're at the same speed. Or if they both reach the bottom, they're at the same speed. Because every point, they've reached the same height displacement. Okay, so if they've gone through the same height displacement, they'll be at the same speed. So when they both reach there, they'll be at the same speed, but will they reach there at the same time? We're going to talk about that, okay? They will not reach there at the same time, but when they both get to those heights, they'll be at the same speed. They won't reach the bottom at the same time, but when they both get there, they'll be at the same speed, okay? We'll talk about that in a second. The two other ways to find kinetic energy is we also know kinetic energy is equal to the change in potential energy, right? So change in K, right? We're still looking at the change in K for the skaters, but I'm showing you 3 different ways to do it because you have to have all these in your head, right? So we also have the change in K is equal to the negative change in U because we know work. Remember, go watch the work concept video if you don't know, but work's equal to the, right, change in negative U, and work's also equal to the change in K. And because work's equal to both of these, we can make them equal to themselves, right? Now, there's initial gravitational potential energy. When they both reach the bottom, there's no final, right? So that becomes 0, and we can see the change in kinetic energy is equal to the initial mgh. Because when they both reach the bottom, there won't be any gravitational potential energy. That's also equal to their change in kinetic energy. So we see that it can also be based off their height displacement and their weight, or just their change in potential energy as well is equal to the change in K. So another way to look for the change in kinetic energy. But here we can see it's the mass and the height, right? But just another way, it depends on what you have. You can use any one of these 3 options to solve for the change in kinetic energy or the amount of work done based off the variables you want to use. This one lets you look at speed, this one lets you look at height displacement, and this one right here lets you look at the slope, right? So we know that if we look at the work done just coming down, the force, right? We draw these free body diagrams for both objects down the ramp. There's no friction. The only force is going to be down the ramp, and that's mg sine theta for both of these. You know this from a box on a ramp. So I'm not doing the whole free body diagram, but you know that when there's no friction and something's sliding down an inclined plane, the only thing pulling them down is mg sine theta. So we know the net force, right? Because normal force and mg cosine theta are both 90 degrees of displacement, so they're not doing any work. So we know the only force doing any work here is mg sine theta. So we replace the force with mg sine theta. Cosine theta turns into positive 1 because that net force and displacement are going to be in the same direction for both of them, right? So that turns into positive 1, right? And the force turns into mg sine theta because that's true for both of them. And the displacement will be there as well, right? So what we end up seeing is that the work of the change in kinetic energy can also be written in terms of the slope instead of the height, where we look at the weight of the object, so the mass is important, the theta, and the displacement. So here we can see again that the change in kinetic energy for this person is still larger. Here we can see the change in kinetic energy is larger because mass, right? Their velocities will be the same down here, but this person has a larger mass than this person, so they have larger change in kinetic energy. This is proving the same thing. Same height displacement, but since this person has a larger mass than this one has a larger, right? M1 has a larger change in kinetic energy than M2. And here we're saying, right, this has a way larger angle than this one. So theta is larger, no matter what this displacement is, right? Theta is larger, mass is larger for this person over here. So the change in K must be larger for this person over here, no matter how we choose to look at it, okay? So that's the thing. The work's the same for both skaters, right? But what we can see is that when we look in here, the change in K, right, is larger for M1 than it is for M2. So let's make sure you understand what we're saying for these people. Okay, we're saying that K1 is larger than K2, the kinetic energy. We're also saying the change in K1 is greater than the change in K2, right? This is M2, so that's K2. This is M1, so that's K1, right? So M1 has a larger kinetic energy and a larger change in kinetic energy versus K2. We're saying that's two different things we're saying. It has a larger kinetic energy and has a larger change in kinetic energy, all right? So that's this video. I hope it was helpful. Oh, there's one more thing. I'm so sorry. The time. So do they reach the bottom? Well, we know that acceleration dictates the rate at which we are motion, right? It dictates the rate of motion, right? So we know if these guys will reach the bottom at the same time if they have the same acceleration, okay? If they don't have the same acceleration, they won't reach the bottom at the same time because acceleration is the rate at which your motion changes. If they have different rates, they're going to speed up. Even though their speeds will be the same at the bottom, one's going to speed up faster than the other. So one's going to make it to the bottom versus the other. Their velocities will be the same, but they won't reach the bottom at the same time because their accelerations aren't the same. If you don't remember that, let's just refresh because we learned this with the box and a ramp, right? So we can start with FMA, right? The acceleration for both these guys is going to be down the ramp because that's the net force, where mg sine theta is going to be the only net force down the ramp. We're ignoring friction, right? So mg sine theta is equal to ma. Same thing for this skater. Mg sine theta is equal to ma, okay? Then we see the masses cancel, and when the masses cancel, we're left with just acceleration is equal to g sine theta. So we see the acceleration, the rate at which they're going to move down here, the rate at which they speed up down the ramp is based off of the theta, because they both have the same g. Well, this one has a much larger theta than this one, so that means it has a much larger acceleration, which means it's going to get to the bottom faster. Okay, that's what that means, and we know because it has a much larger theta, we can already say that. But when we put it into this equation, right, this kinematics equation where the initial velocity is 0 for both of them, right, so we end up with an equation of final velocity equals acceleration times time, and then we solve for time where acceleration comes under the bottom. So for both of these skaters, they're both going to have the equation for time as Vf over g sine theta, where we see the time, since they're both going to have the same velocity at the bottom, the time's dictated by their theta. All right, this is going to have a much larger theta, and we know that the larger the number is on the bottom, the smaller this is, okay? So this is going to be much larger for M1, so the time's going to be much smaller, right, in comparison to this. This is going to be a larger number than this one, so time is going to be small. So again, larger number down here, smaller here. This is going to be a smaller number than this one. Sorry, I said that backwards, so that means time will be larger. So this one, this person will make it down. It'll take this person longer to get to the bottom than this person. That's what that's trying to say. But again, go back and watch this and know all this, write all this down because you need to know all this. It's important that you're able to walk through these steps and do this work. I hope this was helpful. I'm super proud of you. See you on the next video.